Hi, welcome. Today's topic is the internal forces of a frame with an oblique bar. This is the first example. There is such a frame. It even has a joint here, but it doesn't change much in the calculations. You'll see right away how to calculate such a frame with a joint. So, what do we have? From above, it is loaded with a continuous load. Here is some horizontal concentrated force, a vertical concentrated force on the oblique bar, and a moment in the middle of the vertical bar. Of course, the first thing we have to do is standard procedure. Calculate the reactions. I've calculated so many of these reactions in this series that I won't dwell on this specifically here. I'll outline the equations for you, and we'll see what the results are. And here is the moment at the joint on the left side. In Gerber beams, you can look at the video. I talk about the moment at the joint on the right or left side there. Here, I did it on the left side. I immediately calculate this reaction equation VA. Then the sum of moments for the whole system at point F, which is at this support. And from this equation, we found that the moment at the full support is equal to 0. The sum of the projections on the horizontal axis and the sum of the projections on the vertical axis. And we have calculated reactions. We can perform a check. I did a check here by summing up the moments at the joint for the entire system. And indeed, the left side equaled the right. Now the problem arises for the oblique bar. We have to resolve forces into the direction normal to the bar and into the shearing direction. That is, forces parallel and perpendicular to the bar. The parallel ones are normal forces, either tensile or compressive, and the perpendicular ones are shearing forces. So we definitely need to resolve this reaction VA, which came out as 3 kN, into a direction parallel and perpendicular to the bar. And this is actually the only difficulty, which is a new thing in frames with an oblique bar. I always do it like this. Here we have the direction of the bar. Between the direction of the bar and the horizontal, I marked the angle alpha. That is in this place. And I also marked the vertical. And now if I extend the direction of the bar, extend the vertical and horizontal, and drop a perpendicular to this direction of the bar, something like this will form. And here this direction I am now showing is the normal direction to the bar, meaning tensile and compressive forces. While perpendicular to it is the shearing direction, where there will be shearing forces. And now from trigonometry, if we look at this right angle, here is the complement to the right angle, which is 90 minus alpha. We look at this because between the direction of the bar and its perpendicular is obviously a right angle. Here we have a complement to the right angle, so here must be a right angle, and so on. Every other angle will be angle alpha, so we can mark that every other angle is angle alpha. Now we break down, well, we will definitely have to resolve this 3, because we will be going here from the left side to this slanted bar, so we will have to decompose this reaction via, meaning this 3. So we place it on our drawing and we want to decompose it into the cutting and normal direction to the bar. And now, as I have already mentioned in previous videos, the component adjacent to the angle, which will be this one, is with the cosine of this angle. So we need sine and cosine. Sine, often found in triangles with slanted bars, will be 3, 4, 5, just as we have here. Sine is the opposite of the angle to the hypotenuse 4 to 5, which is 0.8, cosine 3 to 5, 0.6. So the component adjacent to the angle is with the cosine of this angle, so we have 3 times cos alpha, meaning 3 times 0.6 gives us 1.8. And here we have 3 times sin alpha, which means 3 times 0.8 gives us 2.4. I usually don't draw this on the drawing I make here, but somewhere next to it. And now for this drawing, we can apply the same procedure to the second force, which we will also need to decompose because it is on a slanted bar. So in the same way we place it, we have the cutting direction, the normal direction, the angle is at the cutting direction, so this force will be with the cosine, which is 0.6. 6 times 0.6, which is 0.6, and the normal force will be with the sine, which means 6 times 0.8 gives us 4.8. And we have these forces decomposed, and we will draw the diagram on this basis, that we will first go to the slanted bar from the left side, then to the vertical bar from the bottom, and to the horizontal one from the right side. Of course, this can be done in any way, but I will do it this way in this video. So here we already have drawn, instead of reactions I have written their values, that 8 That horizontal reaction was to the right, but a minus came out, so I drew it to the left with a plus. Bottoms are marked, so we know everything. These are our decomposed forces. This is our cut and this cut here, which will be between point A and point B, meaning we only see these 3 kN, and when we move further with the cut, we will already see the 6. So this cut is the second cut on the slanted bar, imaginary section. And we must remember the marking, meaning having the bottoms at the bottom if this was a beam. On the left side, the signs are positive. On the right side, the signs are positive, meaning when we cut the vertical horizontal bar at the top, looking at it from the right side, it will be the cut. When we cut the vertical bar from the bottom, it will also be the cut, of course, if we mark the bottoms from this side. If we mark the bottoms from the other side, the signs will be reversed, but it will ultimately be the same. So marking the bottoms does not matter. So as I said, we make a cut. So here, really, 2, 1, 2. If there is a need, here 2 will be only at, if there is a moment, and here the cut. We look from the right side, and here on the slanted rod, here we will always have to do it twice. Okay. I think we have everything. We can draw the graph. So first, we are interested in drawing the normal force graph, meaning compressive and tensile forces. By doing this on the slanted rod, looking at this section, meaning from this point hiding everything on the right side, and we see only the supports A, we are interested in the normal force to the rod. So here will be only the normal component of this triple, meaning 2.4. It compresses, meaning the direction is opposite to what is shown here, so it's negative. Then, as we move to this second section, besides having the 2.4 that compressed, an additional normal component from 6 appears, which is 4.8, and it stretches. So we simply have to sum these two forces then. At this point, where the component of 6 is, there will be a jump of 4.8 in the positive direction, because the force has a positive direction when looking at it, or it stretches when we look at it. But in any case, there will be a jump of 4.8 in the positive direction. I think that's clear. So first 2.4 negative, because we have the support component, and then a jump of 6 in the positive direction. Then we look at this vertical rod. And here along the entire length, there is no other tensile or compressive force than this 15. So there will be a constant value of minus 15, the opposite direction to positive, and besides, it compresses the section, which is why it's also negative. And now we'll look at the horizontal rod, but from the right side. So we cover everything on the left side of this section that I've drawn here. We discard all that and look from the right side. We are interested in parallel forces, meaning those that stretch or compress this horizontal rod. So only horizontal forces interest us. The only horizontal force looking from this section to the right is this 8, and it acts primarily compressively. It compresses this upper rod. If we move it here parallelly, which is what we have to do. And also it has a direction opposite to the positive indicated here. So we have a constant value of minus 8, because there are no other horizontal forces on this rod. We have drawn the normal force graph. Next, we will start drawing the shear force graph. And here we start similarly with the slanted rod. So now we are interested in the direction perpendicular to the rod. Here, perpendicular is this 1.8 from the support. So we'll have a jump of 1.8. It is positive consistent here with this direction. I'm moving this mouse a bit, consistent with this direction. And then when 6 appears, 3.6 appears opposite to the direction. So there's a negative jump in the negative direction of 3.6 comma, so from a positive 1.8, minus 3.6 at this point, jumps to negative 1.8. Then we go to the vertical rod from the bottom, and here we look at what shearing forces we have. The shearing force is this 8, and no matter how we shift the cut to the end, there is no other shearing force than this 8. Its direction is a positive direction in this section. So, over the entire length of the rod, we have a positive 8. And now the horizontal rod. And here, yes, we're also looking from the right side. If we stood at this vertex, made a cross-section and looked not infinitely close, but from the right side, the only vertical force would be 15. Then, as we move away with the section, more and more continuous loading appears. So here there will be a linear descent. Remember from previous videos, I talked about this many times. So we have a jump of 15 at this point. Now the question is whether it is a positive 15 or negative. Here we have marked positive directions. The positive direction is down. 15 is opposite, so it is negative. So we first have a jump of negative 15, because the concentrated force is 15. And then the graph will change linearly. Oh, the resultant value from continuous loading. The resultant from continuous loading is 3 by 4m, which is 12. So, from a negative 15 by 12. And now the question in the positive or negative direction. In the positive direction, because continuous load acts down, and the positive direction is down. So from negative 15 plus 12, which is to negative 3. So we have the shear force graph. We can move on to drawing the moment graph. So let's start from the inclined rod again, returning to the left. And we have to do it in stages. Or maybe we'll do it using the moment calculation method at a point. The moment at point A, as we know well, is 0. Here there could be an initial moment if there was a moment applied to the support. But there isn't, so the initial moment is 0. Then the moment at point B. So here you don't need to use these components. You can, but you don't have to. So now, the moment that force 3 creates at point B, because only it causes a moment from the left side, is 3 positive because it is clockwise. And on this side, a positive moment is indicated here clockwise as well. On this arm, this is the direction of action, this is the arm. So on an arm of 1.5 to the middle of the beam, that is 3 times 1.5. This is the moment at point B. The moment at point C follows the same principle. 3 times 3, which is force 3 on arm 3. Minus, because anti-clockwise, 6 on arm 1.5. 3 times 3 minus 6 times 1.5. Well, we know that at a joint, in beams, both beams and frame joints, the moment nullifies. Therefore, the moment at point C should be 0. If it doesn't come out to 0, a serious consideration is needed. So now we know everything. 4.5 in the middle, 0 at the end, linear function. Now we start on the vertical beam. Looking from the bottom, do we have any initial moment? It could be, but here, it's rare actually, but here in this fixed support, it turned out to be 0. The fixed support moment came out to be 0, so no initial moment. So, just like on this sliding support, we will have an initial moment of 0. If there was any moment, we would start from its value. Then we calculate the moment at point E. But be aware, because there is a concentrated moment applied at point E. So here, there will be a jump of the value of this moment. Recall, if a shear force is applied on a beam, or frame, there is a jump in the shear force diagram by its value. If a moment is applied on a frame or beam, there is always a jump in the moment diagram by the value of this moment. Hence, we remember that there will be a jump here. So first, we will calculate the moment at point E from the point F side, not infinitesimally close. So not including yet the moment applied at point E. Then we will calculate as if considering this moment. Again, the moment at point E is caused only by this 8. The tensile force does not cause a moment. So the 8 definitely does 8 times 2, 16. This is a clockwise 16. But on this side, anti-clockwise moments are positive. So we have from 0 to minus 16. Then we will have a jump. And now again, is this moment 4, viewed from below, positive? It is right twisting, which means it is just as negative as the 8 on arm 2. So there will be a jump again into the negative side. So it will be minus 16 and a jump of 4, which is to minus 20. So the moment at point E from the side of point F minus 8 times 2. The moment at point E from the side of point D, which is the minus 8 times 2 and also minus 4. Now the moment at point D, well, that is minus 8 times 4 and minus 4. This is the moment here at this node, the moment at point D. Well, actually from the side of point E. And now, of course, so how much does it come out to? Minus 8 times 4 is, well, maybe the graph will look like this first. 16, jump by 4, 36. So now it's worth checking. So calculators at the ready. First, we can immediately write down from the node equilibrium 36. But maybe it's worth checking if this 36. Counting from the left side will also come out to us. So 3 times 7 minus 6 times 4, 5.5. 8 does not act, minus 3 times 4 times 2. Does this equal minus 36? Calculators at the ready, and let's calculate. Then the same, the moment in the joint. From the left side, we have already calculated that it is 0. Let's check from the right side. Calculating the moment at point C from the right side, we have this. Minus 15 on arm 4, plus 8 on arm 4, plus 3 times 4 times 2. We check if it comes out to 0. And later plus 4. Not sure if I mentioned, probably not. And this will be the moment in the joint, viewed from the right side. But generally we know that here from the equilibrium is 36, here 0. Should there be an extremum here on this beam horizontally? Yes, no, why not? Here on the friction force diagram there is no change of sign under continuous loading, so on the moment diagram there is no extremum. And the parabola is bent under continuous loading. And that's it, we have the diagrams drawn. If you have any questions, feel free to ask them under the video. None will remain unanswered. I encourage you to like our Facebook profile. Of course, visit our website. As for examples with frames with an inclined bar, there are over 20 of them. So it's worth it. Solid learning material. And don't forget to subscribe to us. Warm regards, bye.